Third and final circuit analysis theorem, Norton's theorem. Norton's theorem says any active network having two terminals A and B can be replaced by a constant current source of current IN. Let's revisit these notes. And an internal resistance Rn. The value of IN is equal to the current that would flow between the terminals A and B if they were short-circuited, and the value of the resistance Rn is the resistance of the network measured between the terminals A and B with the load disconnected and all sources of voltage or current replaced by that ideal internal resistance. Resultant Norton circuit looks like this. So Thevenin circuit is a voltage source and a series resistor. Norton circuit is a current source and a parallel resistor. Okay? So what we're going to do is go through an example like we did for Thevenin's as a way of you being shown, learn how to do the process. Again, it's not that different, so it's just a matter of following the steps, which are steps for Norton's theorem. Short circuit the branch AB. So you take your resistor out and short it. Determine the short circuit Norton current flowing in the branch that you've shorted. So that requires some DC theory in this case, Ohm's law, etc. Then that will give you a Norton's current, or the value of IN, and then you remove all sources of EMF and replace them by their internal resistance. If a current source exists, replace with an open circuit. Determine the resistance looking in at the break between A and B. Then you can determine the current flow in a resistance from Norton equivalent circuit using either the current divider or other methods if you prefer them, like finding the terminal voltage and calculating it from that. Okay? So, let's have a look at an example. Using Norton's theorem, calculate the current flowing and the power dissipated in a 30 ohm resistor. So we're looking at R4 here as our resistor of interest. However, there is a caveat with Norton's theorem that you have to take out everything in that leg. So you have to take that R1 out as well. Okay? To take everything out that's in the leg that you're interested in. So we do that. First short the complete branch containing the 30 ohm resistor. We mustn't forget when we put things back at the end, we must put that R1, that R3 back in again. Okay, as well as the load resistor. So we short circuit across the two terminals. Okay, so our two terminals A and B are going to be there and there. Right, now we can say that's equivalent to the voltage source and just the R1 resistor, because if this is an ideal short circuit, all the current is going to go that way and none of it's going to bother going through the 20 ohm resistor, because this is perfect. This is a perfect short circuit, therefore we've effectively shorted out that resistor. No current will go through it. You all understand that? Yeah? So from that, the short circuit current flowing through our shorted wire between A and B, this is the current we're interested in. That's IN. IN is equal to VS divided by R1. 24 volts divided by 5 equals. I really ought either made that 25 or the resistance 6 really, didn't I? But never mind. What is it, Jack? 4.8? Is that exact? 4.8 amps. Okay, so in our final Norton's equivalent circuit, we're going to have a current source of 4.8 amps. There it is. So write that in there now. 4.8 amps. We'll do it now. Got to remember, we've got to put that R3 back in there, as well as the R4 resistor of interest. That one was 30 ohms. Just remind me what this one was. 5. Okay. So we've found IN. Now we've got to find RN. We'll come back to that in a minute anyway. So RN is the resistance looking in. So we've replaced the voltage source with the short circuit here. Short VS. Well, yeah, if you look at that circuit, take that short away, yeah, looking back in there as a parallel circuit between the 20 and the 5. If you take the if you short the voltage source out, agreed? Yeah. So Rn is equal to R1 R2 over R1 plus R2 4 ohms. So take that 4 ohm value and put it in here. And we can use any method we want to find the current ultimately flowing with the original question. Current flowing and the power dissipated in a 30 ohm resistor. So we want to know what this current is, IL. How would you do that? We can calculate, there's ways we can find this voltage, VRN, there. How can we do that? Because that voltage is also going to be the voltage across that pair of resistors, isn't it? Yep. Sorry? Well, you could do, but the question asks you specific information about that one resistor. Yeah. So you need to be careful. How am I going to calculate that voltage? This one here, V. I'll just write that a bit neater. This VRN. What I need to do first. Which is Rn times R3 plus R4, because they're in series, yeah, divided by Rn plus R3 plus R4. Four times 35 over 39. Will it come out to, Lewis? Therefore, VRN is equal to you've calculated what you turned this into is one current source and one total resistance. You joined all that into one, so this voltage is going to be the volt drop across there. So you've got 4.8 amps and a 4 ohms. IN times RN. IN is 4.8 times 3.59 equals 17.23 volts. So we now know we got 17.23 volts across that pair of resistors. So therefore the current in a load is VRN over R3 plus R4. That's 17.23 over 35. Naught 0.49. Power R4 is 0.49 squared times the 30. That's where we're going to focus on the one resistor, because half the power dissipated in R4. What we got? 7 point watts. Okay, so Norton's theorem process is very similar to that of Thevenin's, except you're replacing the open circuit voltage at terminals A and B with the short circuit current for IN, and you're ending up with an ideal current source in parallel with Rn, as opposed to an ideal voltage source in series with RT. Okay? The rest of the process, what you replace sources with, is exactly the same, that ideal internal resistance. Okay? So, in your notes, There's a second example with two sources. Okay, and then in the other notes that I gave you, there are some further examples. So I gave you pack 2 weeks ago. There's a section on Norton's theorem in there. There's some other examples. What you need to do now is practice these techniques so that you can do them and understand that process. Because like I say, I'm testing you on your knowledge of the process as much as your ability to be able to do the maths. Alright? So I'm going to leave you to have a go at some of the questions I've given you now.